Okay, so thank you to the organizers. I've already had some great conversations at this conference. And just to frighten the person who was asking me whether I was going to use chalk, I'll start by picking up some chalk, but we won't. Actually, if you don't want to be so disgusting, you could do this version, which is, anyway. But no, I won't use chalk, but something that looks slightly like chalk. So I'm going to talk about Abelian critical exponents. And based on a few conversations, I reference some older work, but I probably could have had many references to Arseny Schur, who knows many things about Abelian exponents, but there won't be any, so my apologies to Arseny. And also, I talk about de Jean, so I probably should have had a lot of stuff about Arturo Carpi. So those aren't in the talk, so apologies in advance. However, so this is something perhaps not necessary for this audience, but a k-power is a word with period p and length l, such that L divided by P is equal to K. So here is a 7/2 power. And just like in the talk by Pascal, 14/4 is 7/2. So that's why. Anyway. Whoops, wrong direction. My apologies. Now, when we talk about abelian k-powers, the order of letters doesn't matter anymore. So here, when I look at A, B, C, D, that's the same as CDAB, which is the same as CABD. So in an abelian sense, this is the same thing 3 times in a row. So this is an abelian 3-power. Now, going back to prehistory, and this is not quite as far back as 2A, but pretty far back, 1957, Erdős suggested in the Michigan Mathematics Journal there could be an infinite sequence on 4 letters containing no abelian 2 powers. So it's actually in this second paragraph. The first paragraph is somewhat humorous if you've ever tried to look at the literature on square-free words. Everyone thinks they're inventing square-free words. And here Erdős figured that Peltisson and Sutherland, who I really have never heard of, discovered the first ternary square-free sequence. But we'll ignore that. And here Erdős is saying, if I have k letters, how long a sequence can I have before I'm forced to have 2 adjacent blocks, each of which is a rearrangement or an anagram of the other? And so he conjectured, probably you can't go farther than 2 to the k minus 1, but then he and De Bruyn showed that was false. It's not known whether on 4 letters you can have an infinite sequence. Erdős's, many of his papers are just these long lists of problems. You can see this was problem number 28. There's another publication from 1961 where he starts to have some more information and definitely conjectures that you can have an infinite sequence on 4 symbols. So this problem, avoiding abelian squares, kept people busy for 35 years. So infinite sequences not containing abelian 2 powers were found by several people, and the alphabet got smaller. So Evdokimov in 1968, on an alphabet of 26 letters, found something with no abelian squares. Then P.A.B. Pleasance in 1970 showed that you could have abelian square-free sequences on 5 letters. And then finally, Karenin in 1992 got down to alphabet size 4. Okay, so this is some of the history. Now let's go back to ordinary non-abelian powers. So for k between 1 and 2, a k power has a certain form. It looks like x, y, x. And the length of x, y, x divided by the length of x, y is k. So in other words, x, y is the period. The beginning x is repeated. And there you go. So with this observation, looking at fractional powers, you can define abelian fractional powers. So instead of having x, y, x, I'll have x and y and an anagram of x. A little bit before I get to that. For a given word, w, its critical exponent, so this really makes sense for infinite words w, is the supremum of the k, so that w contains a k power. And the repetitive threshold for an alphabet is the infimum of the critical exponents for words on that alphabet. And de Gennes conjecture, in 1972, de Gennes conjectured that for integers, the repetitive threshold will be n divided by n minus 1, except for a couple of special cases. I find it amazing that de Gennes made this conjecture, because de Gennes actually proved this for 2 and, for 2, it's 2, the 2a Morse word has critical exponent 2. And then de Gennes proved this for a 3-letter alphabet, the critical exponent is 7/4. And then here's the conjecture for every other alphabet. And this turned out to be true. So this took 37 years to prove. I should have put Currie on this slide, because Currie basically solved the problem, except for finitely many cases, and then Rao finished it off. And independently, Narad Rampersad and I have a proof. So there's de Gennes' conjecture, 2008, or 9 or 10, somewhere around there, from the proof to the publication. So back to abelian stuff. So an abelian k-power is the word x1, y, x2, where x1 is an anagram of x2, and the power is the length of x1, y, x2 divided by the length of x1, y. So here's an abelian 3/2 power. I have this word, x1, then a little piece y, and here's x1 again, except it's scrambled. Right? So this is an abelian 3/2 power. And so we can immediately generalize in the obvious way an abelian critical exponent, ACE of w, and an abelian repetitive threshold. And so here's an open problem. And so this is probably a hard open problem. I have 3 open problems in this talk, 2 of which I probably shouldn't tell you, because several of you are young and full of energy and can just go solve them. And I'll tell you how to solve them. And if you don't believe me, actually before I sort of tortured Narad into helping me finish off de Gennes' conjecture, I went to several conferences and I said, someone should prove de Gennes' conjecture now, because Arturo Currie has polished it off, and here's what you should do. And I went around to all these conferences and no one did it. And then I was mad and I said to Narad, okay, well. So anyway, I'm not sure what, if we look at abelian critical exponents, what is the proper conjecture? I really have no idea. Arseny probably has some ideas. Now the thing about abelian repetitive threshold, it's actually very intimidating, because Karenin, remember Karenin found that you can avoid abelian squares on a 4-letter alphabet, but his morphism, each letter maps to something of length 85. So you're not going to look at it and say, oh, well, obviously here's how this morphism comes about. So I don't know what the repetitive threshold should be on 2 letters. Karenin tried for years to improve his construction. and he exhaustively searched a lot of things. He found a few other morphisms, but longer morphisms. So it's intimidating. And it's not obvious that you can get abelian critical exponents less than 2. But with Julien Cassin in 1999, we showed that if you have a large enough alphabet, you can make the abelian, if you have a large enough alphabet, you can make the abelian critical exponent go down. You can make it go down to 1. But it was not a great construction. So for us to show you can get an abelian critical exponent less than 1.8, you need about 5 to the 485 letters in your alphabet. Yeah, that's challenging to do computations with. By the way, I put the exclamation mark in brackets so that you could tell I was very excited, but that you would know it's not a factorial. Okay, it's not that big. Okay, so you look at these constructions and you say, well, it appears all constructions are just totally unreasonable. Karenan's construction has 4 times 85 is the length of the morphism. This thing of Currie and Cassin is ridiculous. So in order to persuade people to look at this, I guess we have to find a construction that is not so stupid. So that's what we have today. So here is a reasonable word where the abelian critical exponent is less than 2. So I have an alphabet with 8 letters, and because I've been hanging around with, see, normal people count 1, 2, 3, 4 up to 8. But if you hang around with computer scientists, then you count 0, 1, 2, up to 7. So here's my 8-letter alphabet. And I have a 13 uniform cyclic morphism. And this is given by f of 0 looks like this. I just have a lot of zeros in here. And I put in the letters 1, 2, 3, 4, 5, 6, 7 in this kind of scrambled order. And I changed this slide. Nerad said, you should explain what a cyclic morphism is. And I thought, really? Yeah, but so a cyclic morphism, as you move up the alphabet, the letters move up. So the image of 1, the 0 gets promoted to 1. The 7 goes up to 0 because we're working modulo 8. The 4 goes up to 5 and so on. And then for the image of 2, 1 goes up to 2, 0 goes up to 1 and so on. So it's a cyclic morphism. And if you iterate this morphism, look at the fixed point. We just apply the morphism over and over again to 0. So I conjectured in 2003 that the abelian critical exponent of this was less than or equal to 1.8. In fact, I may have said it was less than 1.8, but no one ever called me on it. So we'll say I conjectured this in 2003. So now it's a theorem. So I talked to Nerad and I said, we should prove that this is true. So here's the theorem. The word, which is the fixed point of that morphism, has no factor x1, y, x2, with x1 congruent, an anagram of x2, such that the critical exponent is larger than this ridiculous fraction, which is less than 1.8. Okay? And the proof is not hard, and there's an idea which I found kind of charming. So let's look. Oh, and by the way, this is just a bound. Right? So the critical exponent, there's no factor, bigger than this number. So the critical exponent is less than 1.8, but I don't know what it is. So the second open problem is find out what the critical exponent is. And I think this is doable. And if you have energy, you can go and find it. And yes? We have this word no. There's no factor, so that this, okay, good. No, that's okay. I feel better about my earlier jet lag question. With respect. So what is the abelian critical exponent? I don't know, but the reason I don't know is because I'm lazy. Because proving the theorem, you actually have to do this deep search in the word. And when you do the deep search, all of the factors with large abelian exponent seem to be built recursively from other words. So if you stared at it, I think you could figure out the factors with large exponent, and then you'd know what the critical exponent is. So maybe someone will do this before dinner, but we'll see. Here's how the proof works. So in the morphism, the image of 0 has a lot of zeros, but only one of all the other letters. And the idea for this comes from Pleasant's construction. Karenen's construction, I have no idea how his morphism is built. Kiernan doesn't really have any idea how his morphism is built. You just ask the computer and it finds it, and then you prove it works. But Pleasant's construction has an idea. And the idea of Pleasant's construction, the image of A has an awful lot of A's in it, right? That's the idea. And so using this idea, let's see how this works. So the image of 0 has an awful lot of zeros in it. Now suppose I end up finding some abelian power x1, y, x2. And suppose that x1 is long and y is long, right? So then if those are long, then I can parse them in terms of the morphism. So x1 looks like the image of something. Pardon for my shaky hands. I think that's a jet lag thing also. Maybe we can brace this against my body. So I've got the suffix of the image of a letter, and then I've got the image of a word, and then I have the prefix of the image of a letter. Right? So I suppose I have some abelian power. So x1 and x2 are supposed to be anagrams of each other. Well, actually, if x1 has more zeros than x2, then when I look at f of x1, it has lots of zeros. Right? So if x1 has more zeros than x2, then there's lots of zeros in f of x1, a lot more zeros in f of x1 than in f of x2. So I have to make up the difference for these words to be anagrams of each other. So the extra zeros either show up in S2 or in P2. So S2 or P2 have to contribute the needed zeros, but if I have a suffix which has more than one zero in it, then it comes from the image of 0. Right? So that's the idea. So here the notation P1Q1, right? P1Q1 is the image of some letter, and there's P2, S2 is not, or S3. Yeah, there's a Q2 which is not shown. So P2, Q2 is the image of some letter. And if P2 has a couple of zeros, then the letter of which it is the image was 0. So parsing x1, y, x2, we write it so that it's contained in B1, x1, a1, then there's a y in the middle, then there's B2, x2, a2, and what happens is either we fatten up, we take x1 and we either add the b1 or the a1 or both, and we end up having an anagram. One of these words, b1, x1, is maybe an anagram of x2, a2, something like that. So if there was an abelian power in the image, then there's an abelian power in the pre-image. It might not be quite as high an exponent, and we change the length by a little bit. So you pay attention to the lengths. Suppose n is greater than 1, and W contains an abelian power x1, y, x2, where x1 is an anagram of x2. This condition here, where I say that the length of x1 is at least 24 times n, what that is saying is x1 is large enough that I can parse it in terms of f. Then the pre-image of this, x1 hat, y hat, x2 hat, is also an abelian power. So here I have x1 is an anagram of x2 with the hats, or the tildes. And there's a relationship. x1 hat, y hat is it's a lot shorter than x1, y. And the exponents differ by something which is not very much, because my intention is that x1y is large, which means 72 divided by x1y. It's not, these two things are kind of close together. So as I go into the pre-image, the power is almost as big. And here's how we bound the abelian critical exponent. So we start with x1, y, x2. We go back to a pre-image. We go back to a pre-image. We keep going back. And we end up having the critical exponent differing by the sum of a geometric series, which is the sum of the geometric series is where this comes from. So if I know that whenever I have an abelian power where the length is less than or equal to 24n, so I do a search and I find that any abelian power where the period is small, the abelian power is small, then every abelian power is not too much bigger than that. All right, so you can read this on the archive. I would throw all the technical details up, but yeah, this is the idea. And so then we do a search, and this function g, all this is saying is I have some word, which is x1, and then I have to fatten it up a little bit. Now remember, my morphism had length 13, so maybe I add 12 at the beginning, 12 at the end. So I've added length 24, then I take the pre-image. So that's why we have the length of a word plus 24 divided by 13. So if I have a factor of this, and g to the t of the length is less than or equal to 2, then the word is equivalent up to a permutation of the alphabet to a factor of this length. And so if my word contains a factor larger than this, and the length of x1 is less than or equal to 1,000, then f to the fifth contains such a factor. So we search the prefix of this thing of f to the fifth of 0. All the factors obey this. Then we look at the search lemma, and we find that, oh, so there are no factors at all which have a higher exponent and this period. And then applying that gives you the theorem. Boom. So, yeah, so anyway, I think you could probably use this construction to get an upper bound for every n. And here's how that goes. So I have this lemma where I say that if x1 hat contains more zeros than x2 hat, then that affects the prefixes and the suffixes. So that lemma, I only use the fact that there's 6 zeros and only one of every other letter. So you could try other cyclic morphisms that have the same property. So maybe I take a morphism H, I have 0, 1, 2, 0, 3, 4, 0, 5, 6, 0, 7, 8, 0, 9, and here A is, that's a hexadecimal A, okay, so and 0. So we could try things like that, and the same lemmas about the prefixes are going to work. Unfortunately, this particular morphism doesn't work because if you take h squared of 0, you'll have the image of 2, 0, and that contains 1, 2, 0, 1, 2, 0, which is a square. So, which is the same reason that in my morphism I had to scramble the letters. I couldn't just go 0, 1, 2, 0, 3, 0. So you have to scramble it so that when you iterate it and you do the search, things work out, right? So I hope my goal in presenting this problem and thinking about this problem is to make you think that looking at Abelian critical exponents, it's not totally intractable. Just maybe don't start with the 4-letter alphabet. That's very intimidating. As soon as you move up to an 8-letter alphabet, oh, this construction's not so bad, and you can put a bound on the critical exponent, and then, you know, as I say, one of you can figure out what the actual critical exponent is, and then someone else can say, well, this guy's very lazy. I mean, here I found a bunch of morphisms that work for alphabets of size 9, 10, 11, 12, or maybe for all alphabets, and then you can put an upper bound, and you can say, you know, here I found an upper bound for the Abelian repetitive threshold. So that's it, and thank you.
So, hi, James. Thanks for the very nice talk. I have a question related to the definition of these Abelian fractional repetitions.
Okay.
So, I mean, probably you will qualify it as a jet-lagged question, so I apologize in advance.
Excellent.
So when you take this, let's say, you know, Abelian powers between 1 and 2, you say that they have the form x1, y, x2, where x1 and x2 have to be Abelian equivalent. How would you define it for, you know, repetitions between 2 and 3?
I would ask Arseny.
So I mean,
you know, the thing is that if you look at ordinary powers, if I have a word which is a k power and I remove the last letter,
yeah,
I get something that's almost a k power. But you don't have this property for Abelian repetitions. It's
exactly.
It's nasty. It's sort of not local in the same way. There's challenges. You don't have the same sort of symmetries and nice properties. I was complaining to Jeffrey Shallot about this, and you know, he had a different definition for Abelian powers, and I said, well, it doesn't have this nice property, and he says, well, you have to give something up. But yeah, so I don't. Arseny, do you have a definition for powers larger than 2 that makes, you know, it seems
okay, I have a few, of course.
Yeah, that's what I thought.
Quite a few. Yes. Yes. Okay, so there are more than we considered, in fact, but we put a strict restriction. Then when you have something which is in length coincide with a integer Abelian power, then it should be an integer Abelian power, because otherwise you can have much more. And if we put this restriction, so if you have 3 times a period, it should be exactly Abelian cube and nothing else, then there are 3 different definitions in our paper from 2012, like that. And for example, the 2 main approaches are as follows. First, you suppose that you should be asymmetric anyway. Suppose you have a integer Abelian power from the left as a prefix. And then you have some suffix, with some restriction on its letters. And two approaches are, the first approach is, okay, this suffix should have its paric vectors, the number of occurrences, upper bounded by the occurrences in the full period. Yeah, okay, yes, like a jumble subsequence. And another one, it should be equal to the prefix of, say, of a prefix or of some other. This is stronger restriction, but when you come close to the integer value, then everything converges to this integer value. But in between, this should be different, and this can give you different values of abelian critical exponent, but of particular strings. But what about abelian repetition threshold? Nobody still knows a single exact value.
Yeah. At least I'm hoping that having a simple construction that gets less than 2 should be helpful. And I didn't mention, you know, there's so much prehistory. There is a very nice paper by Decking where he shows you can avoid abelian cubes on 3 letters, abelian fourth powers on 2 letters, and just it's very nice. So this would also probably be tractable working on alphabets of size 3 and 4 if you could agree on which definition you wanted to use for, you know, critical exponent.
Okay. Other questions? Yes.
Okay, so your conjecture is that was that this repetition threshold for this word was the critical exponent for this word was less than 1.8, and you prove 1.79, but you stop the computation when you proved your conjecture,
yes.
Right? Like you could go further.
Yes, essentially what happened was you know, the real problem is the short words. You know, you can't, if you pick a morphism and then you do it badly, then I take some word of length 2 and it gives me an abelian square. So I found this word and I said, well, this seems to behave well on the short words. I think this works, and I think here's the abelian critical exponent less than 1.8. And so then I want to prove it's true. And so you'll notice in the search, I have to go up to length 1,000, right? Because I'm committed to this value 1.8. So I'm trying prefixes, and oh darn, I have to go further and further, and then so yeah, so it's.
I guess the reasonable conjecture would be that the correct value for this one is probably closer to this 1.713, right?
Yeah, it's like I said. If you actually look, so do the search, look at where the critical exponent bumps up. Those things are all recursively related to each other. So you sum a geometric series. It's presumably a rational value. So it's just I'm a lazy person, but yeah. So and then this all surely generalizes. Although the question of what the actual, call it a de Gennes conjecture, don't know how to approach that.
Yeah. Just to continue discussing, what's the largest known Abelian fractional power in this word?
This word? You know, I would have to double check the output of my program. I think it's. I think actually, if we go back to the absurd fraction which I displayed, it's probably 87677 or something.
Okay.
Or 6, so, maybe whichever direction. So yeah.
Very close to this.
Yeah.
Okay. Other questions? Yes.
Is there a reason that you are looking words with tiny critical exponent in the very particular set of substitutive words?
So, sorry, say again?
Why are you looking for small critical exponents, Abelian critical exponents, with substitutive words?
Well, I don't know any construction which has been used to show you can avoid abelian powers by any other method. The Lovász local lemma doesn't work in this abelian context. I mean, when I learned about the Lovász local lemma or the entropy compression or these methods, I thought, oh yeah, I should use that to prove something about, abelian things. But when you use the Lovász local lemma, what happens is you end up with an infinite product, and then you take the logarithm, and then you have some series, and then it's bounded and it converges. But the kind of series which you get for abelian things don't converge. Mathieu, have you ever proved anything about abelian stuff using entropy compression or anything like that?
I think this kind of takes a lot of fit for this.
Yeah, it doesn't converge, right? Yeah. So yeah, I use the morphisms because it's the only thing I know. Now, when Kärnän spoke in Turku at Words in 2003, he reported that he had searched all of the cyclic morphisms up to some very large length. And so, of course, I put up my hand and I said, well, why would you look at cyclic morphisms? Because for ordinary repetition, I think the shortest cyclic morphism to avoid cubes on 3 letters, I think is length 12, I think. I'm not 100% confident of that. Whereas, of course, if you take this, 1 goes to 1, 2, 3, there's one of length 6, just total length 6, which is not uniform. So I suspect you can get better results which aren't uniform, but it's so much easier to work with cyclic morphisms.
Okay, so I think now it's lunchtime, so we have to stop the questions here, but there will be plenty of time after lunch if you want to ask new questions and maybe solve some of the open problems. So I think we can thank James again.